All right. Good morning, everyone. So we are recording now. I just want to go over one argument again from yesterday, which we just discussed, but I wasn't recording then. So let's just remember what we are trying to do. So towards the end of yesterday's lecture, we discussed a particular observation. So I want to write that down again. Um, So what is this? What we did is, for a particular vertex in this graph, we considered the vertex t arbitrarily. It doesn't matter. I think this is, I don't want this green colored edge. Okay, right. So for a particular vertex t, what we did is we reduced the edge, the cost of each edge by exactly 1. Okay, so I'm going to put k equal to 1. And for all edges, for each edge incident at this particular vertex, what we are going to do is we are going to put a new cost, which is the old cost. So the original, maybe I just called it C of E. And I'm going to subtract this quantity. Okay, I could also add it, doesn't matter. Okay, so don't focus on whether I'm adding or subtracting. Okay, so now what I want to point out is that for every perfect matching, for each perfect matching of the graph G, the new cost of that perfect matching, remember the cost of a perfect matching is simply the cost of all edges incident at that perfect matching, right? So I'm looking at the new cost. So it will be the new cost for each edge. So I claim that this quantity is the same as the original cost minus k. Does everybody see why this is true? We are simply using the fact that a perfect matching will have exactly one edge incident at the vertex T, for that matter, for any vertex, right? And because we are changing all the edges costs by exactly the same quantity, one of these edges will participate in your perfect matching and the value will change exactly by k, right? Are there any questions or concerns regarding this observation? All right. So if not, we can now apply this observation repeatedly, right? We can do the same thing at every vertex, and because we are using the same procedure, the same kind of statement is going to hold, right? In particular, what you can do is a corollary of this observation is the following. Let's say I choose labels for each vertex, right? So these are real numbers assigned to each vertex. Okay, and now I compute new costs for all the edges. So for any edge UV, the new cost of this edge is going to be the original cost minus the label of the vertex U minus the label of the vertex V. Okay, then I claim that the new cost for any perfect matching is going to be the old cost of the perfect matching minus a certain quantity. Can anyone tell me what I should be writing here?
Sir, should it be twice the sum of labels of all the vertices?
You are close, but there is a. Why should it be twice? Can you explain that to me?
Uh, because each vertex gets counted twice. I mean, again, we are
Is
subtracting.
is it getting counted twice? This is a perfect matching. This is not the whole graph.
Okay, then only once. So just summation of LV over all the vertices.
Right, right, right. Because we are doing the same operation as we did previously, instead of one vertex, we are doing it all the six vertices in this graph. So the observation is going to be, it's simply the sum of all the labels. For every vertex in the graph, you take the label and you subtract that. Maybe let me call this W, just to indicate that it is an arbitrary. Okay. So it simply follows from the previous observation. Okay. All right. So I've given an exercise to all of you. Has anyone been able to do it successfully? Was anyone able to find labels for each vertex so that all the new costs, which we are denoting by C prime here, become non-negative, and the costs of the particular perfect matching that we are looking at, the red colored perfect matching, they all become exactly zero. Has anybody found such labels? Or can you prove that such labels don't exist? No? No one gave it a shot? Okay, well, I did. So, so let me tell you what the labels are. So we are going to put the label. So maybe I'll use a different color for the labels. Okay, maybe I'll put them in green. All right, so here are the labels for the vertices that work. So one is the same here. I'm going to put -2 over here. I'm going to put 1 over here, 3 over here, 5 over here, -2 over here, and 1. Okay, that's it. I found them by inspection. I did not use any magical technique to find them. Okay. Um, Good. And now we can compute the costs of each edge, the new costs. Okay. So can anyone tell me what will be the cost of this edge? RW.
One.
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 1.
One.
Okay, great. Thank you. So I'm going to put that in green color as well. Maybe I'll use a different color. Blue. Why not? So let's put 1 over here. Okay. So all we are doing is we are taking the original cost and we are subtracting the two labels, which are 5 and 1, which are the ends of this edge. Right. If we do this procedure everywhere, what do we get? Well, I wrote them down so that I don't have to work so hard. Let's see. So this is 0, I think. Right. Um, this one is -2. Oh, I think I made a mistake. I wanted the red colored perfect matching to be. Sorry, I think my M was the green colored perfect matching. Yeah, okay. We have been looking at the wrong perfect matching, but it doesn't matter. We have not really been using it. Um, yeah, so the perfect matching we are looking at is actually the green colored one. We wanted to prove that that is a minimum cost perfect matching, right? So that is, it has cost 6, if you might remember. It is this one plus this one plus this one. Okay. So let's first check for these three edges. Their cost should be 0. That was one of the conditions we wanted. We want all the cost of the matching edges to be equal to 0. Okay. So this is 2 minus 1 minus 1, 0. This is -2 minus 1 minus 3 um, plus 3, 0. Right. Good. And let's look at the other ones. This one is 3 minus 1, 2, 2 minus minus 2, 4. Let me know if I make any mistake. It's 2 and 0. And this one here is 0 as well. And this is 9 minus 8, 1. and this one is 1 plus 2, 3, 3 minus 1, 2, and this one here is minus 1 plus 2, 1, 1 minus 1, 0. Okay, so I have a bunch of zeros, yeah, and the rest seem to be correct. Okay, good. So those are our new costs, the ones in blue color, right? As per our observation, okay, let us also compute the sum of all the labels. So these are the green colored are our labels, right? So for every vertex, let us compute the sum. Can anyone tell me what the sum is of the labels?
Right?
It is actually 6. Yeah, it is 6. You probably made an arithmetic error. And that is not a coincidence because our perfect matching had cost 6. And we want its new cost to go down to 0. So the sum of the labels has to be 6, right? Because of the observation that we made here, right? So the sum of the labels is 6. All of the labels are non-negative, which was one of our conditions here. And the labels for the perfect matching we are looking at is exactly 0. So all of the costs are, sorry, not the labels. The new costs for that perfect matching are all 0, right? And so the new cost of that perfect matching is equal to 0. And notice that these two conditions, what do they imply? Can someone tell me what these two conditions imply? So maybe I'll call these, instead of C prime, I will call them C nu.
They imply that the matching that we have found is minimal. I mean,
Right.
minimal,
It's
kind
a
of.
minimum cost perfect matching in this new graph with the new costs, but also in the original graph with the original costs, right? I mean, the graph is
Yeah,
the
yeah,
same, but also with the original costs, right? Observe that these
yeah.
conditions imply that M is indeed a minimum cost perfect matching. As per C new and also as per the original costs. Does everybody see why this is true? All the new costs are at least 0. They are all non-negative. So the lowest you can do is actually 0, right? You can't add a bunch of non-negative numbers and get a negative value, right? So the best you can do is 0, and that is what the perfect matching M is achieving. Okay. So what's the point? The point is that if I am somehow able to magically create these labels, then that would be sufficient to convince anyone that this is a minimum cost perfect matching, right? So this could serve as a certificate. The problem is, do we know whether such labels always exist? Or is it just in this particular graph that we were able to come up with such labels? Okay. If we can prove that such labels always exist, then without looking at all perfect matchings of the graph, we can just give these labels to the friend, whoever you are trying to convince, and they will compute the new costs and they will convince themselves that this is indeed a minimum cost perfect matching. This is clearly better than checking all the perfect matchings, right? Because the number of labels are the number of vertices, which is whatever number. It's not exponential in the size of the graph clearly. And computing the new costs is also, how many computations is it? It's as many as the number of edges in your graph. And then you just have to check these two conditions. So clearly all this can be done very efficiently. So that is the point I want to make here, that what is the key takeaway? If we can prove that such labels always exist, then the problem that we are looking at, the decision problem for minimum cost perfect matching, we can conclude that this problem would belong to NP, because for any minimum cost perfect matching, you know that these labels exist, and so that would serve as a certificate for showing that this perfect matching indeed has minimum cost, right? Once again, such labels means that we want all the new costs to be, so this is the original cost minus the label of u minus the label of v. We want these to be non-negative, and we want for every edge of the matching, of the perfect matching, we want the cost of this edge, the new cost of this edge, to be equal to 0, right? Which is the same as saying that the cost of this particular perfect matching is equal to 0, right? Are there any questions or concerns regarding this discussion? Right? There is a big if over here. I'm not claiming that the problem is in NP. I'm just saying that if we can prove this, then the problem would be in NP. In other words, you can convince anyone that a particular perfect matching indeed has minimum cost. So the big question, the burning question arises that do such labels always exist? What do people think? Any guesses?
I think yes.
Okay. Or for all graphs, you think? I'll give you a hint. It's true for some graphs.
Bipartite or something.
Yeah. Yeah. So it's true for bipartite graphs. And I will now go and define bipartite graphs in case you're not familiar, although we might have seen it when we discussed the organ donor problem. I don't know if I defined them. I think I did not define them. Yes, for bipartite graphs.
So, like the graph which you have shown in the example,
Yeah.
that is not a.
That is not a bipartite graph. That is for a reason. Yes, for bipartite graphs, they always exist. For non-bipartite graphs, they may or may not exist. But there is also good news for non-bipartite graphs. There is a more complex way of showing that the problem is actually in NP. Right? But we will be talking about that in module 4. Okay, so if you can find such labels for any graph, you are done. The problem is such labels may not exist in general for non-bipartite graphs, right? So there is a more sophisticated way of doing things in non-bipartite graphs. And why do we need something more sophisticated? These are the kinds of questions we are going to answer in this course. Does it answer your question?
Yes.
Yeah. Okay. So for bipartite graphs, they always exist. For general, when I say general, I really mean non-bipartite. For general graphs, we need something more sophisticated. Okay. So we will come back to all of these topics in future modules. Okay. But I just want to give you a sense of some of the cool things that we are going to see in this course. And in particular for these questions or for these particular statements that we are going to prove, we will use the theory of linear programming. Okay. All right. So in that case, I want to move to bipartite graphs. Are there any questions or concerns regarding anything we have discussed for min cost perfect matching so far? Notice that all of our discussion until now applied to all graphs. Right? It did not apply just to bipartite graphs. Everything we have discussed applies to all graphs. The only thing for bipartite graphs is the last statement I made, which is that such labels exist for bipartite graphs, and we will prove this. Okay? Good. So if there are no questions pertaining to this stuff, let's talk about a bit more about graph theory. All right, so let's see. Okay, so let's go back to the organ donor problem, because we have already seen bipartite graphs over there. Right. So here we had the organ donation problem, right? And we had some donors and recipients. And what we did is we constructed a graph from this. And we put the donors on the left side and the recipients on the right side. And whenever a donor can donate to a certain recipient, we put an edge. And we also put a cost on the edge. I think I did not write down the costs here, but it doesn't matter. So all the edges are going from the donors to the recipients. And that is what a bipartite graph is. So we can partition the vertex set into two parts, the left part and the right part, if I may, so that all edges go from left to right. Okay? A graph G is bipartite if the vertex set of G can be partitioned into A and B, right? Such that each edge has one end in A and the other end in B. Okay, what do I mean by partitioned? Probably you know, it means that you can write the vertex set as A union B and A intersection B is empty. Okay, good. There is a better way to think about it. So here are some examples. Let's see one, and maybe I'll make one more. Which ones of these are bipartite? Supposing these are G1 and G2, which ones of these are bipartite?
G1 is bipartite, G2 is not.
G1 is bipartite. And one way to see that is to actually color the vertices. So I'm going to start coloring, let's say red and blue. So if this vertex is red, the other vertices, its neighbors, will be blue because they are going to be in the other part. And now I'm going to color this one red, and this one is also going to be red, and finally this last one is going to be blue. And notice that we have managed to color all the vertices red and blue so that every edge joins a red vertex to a blue vertex. Right? So in other words, they are exactly the two vertex colorable graphs if you have seen vertex coloring before. Okay, so these are exactly the two vertex colorable graphs. We are not going to talk about vertex colorings in this course. It's not a course on graph theory. So, okay. And these A and B will often be called color classes. And that terminology comes from the two vertex colorable way of looking at it. Colored classes of the graph G. Okay, and often we will be given the partition. So in that case, we will use the notation G A comma B is a bipartite graph with given color classes A and B. Okay.
Sir, like also,
Yeah.
there's a clique of size 3 contains, sir. Bipartite.
So, sorry, can you repeat that
A
point?
clique of size 3, triangle.
Right. Okay. Right. So you're saying that if there is a triangle, then the graph cannot be bipartite, right?
Yeah.
Okay. That is a good point. So that is one way to see why this graph is not bipartite. Observe that this small graph here is not bipartite because you colored one vertex red, the other vertex blue, and now the third vertex cannot be colored red or blue. And in fact, the same problem will appear in any cycle of odd length. You start coloring, you color this red, color this blue, color this red, color this blue, and now you are in trouble here at the last vertex, right? So in particular, if your graph contains an odd length cycle, I haven't defined a cycle, but you see what it is, and probably you've seen it in previous courses, right? So if your graph has an odd length cycle, then it cannot be bipartite. And in fact, the converse is also true. This is something I hope you would have seen in your previous courses. But if not, uh, I would suggest that you try doing this on your own. Prove that. In fact, I'll put it as a try it yourself. It may appear on your assignments. It's a fairly easy problem. Prove that a graph G is bipartite if and only if it does not have an odd cycle as a subgraph. How many of you have never seen this result before? Can you raise your hand or put it in the comments so that I get a sense of where everyone stands? Okay. Can everyone prove this?
Sir, one question.
Yes, go ahead.
Sir, does having means even cycle guarantee that it will be bipartite?
Well, even if you have an even cycle, let's look at an example. Supposing this is your graph, right? And now I add one more edge. Is this graph bipartite?
No,
Right. Why is it not bipartite?
because if we group, every edge does not go to the other group.
Can you use this? Can you use this point here?
Uh, it does not have an odd. No, it
Is it at least one odd cycle?
It has an odd cycle, yes. So at least one. Can you use this result to explain why this graph is not bipartite? Right. So the thing is, you have an even cycle, but that's not very useful. The problem is that you also have an odd cycle. And once you have an odd cycle, 0, 1, 2, you just cannot color the vertices with two colors.
yes, sir. Got it.
Right?
Yes.
So So even cycles are not problematic, but they also do not prove that a graph is bipartite, because your graph could very well have even cycles and still have odd cycles. Okay. Okay, so anyways, I would like everyone to try this. It might appear on one of your assignments, I'm not too sure, but it is really basic graph theory. So I hope that you have seen it in your previous courses and you should be able to prove this kind of a statement. Okay. This course is going to have a lot of proofs, so I think I should set the expectations right, that this is something you should be able to prove. Right. Okay, so we didn't define what a subgraph is. So for the sake of completeness, in case you are not familiar, a subgraph is any graph that can be obtained by deleting any number of vertices and edges. Right? So for the example we just looked at, if this is your graph G, well, you can delete this vertex. And when you delete a vertex, the two edges incident at that vertex will also get deleted. And you will get this subgraph H. And H is an odd cycle. And therefore, this graph is non-bipartite. Okay? And cycles are connected graphs with each vertex having degree 2. Basically, they look like a cycle. Right? These are cycles. The pictorial representation is much clearer, but this is an equivalent way of defining them. And odd cycle just means that there is an odd number of vertices or an odd number of edges, because the number of vertices is equal to number of edges. Right? So these two are odd cycles, whereas this is an even cycle. Okay? Good. So that's the characterization of bipartite graphs that is worth knowing. We might even find it useful in some later assignment problems or in the course material. Okay? And that is also the reason this graph is non-bipartite. Okay? Good. So why are we talking about bipartite graphs? Well, it turns out that in various areas of graph theory and combinatorial optimization, especially in matchings, bipartite problems turn out to be significantly easier than general problems. So bipartite matchings, bipartite perfect matchings, minimum cost perfect matchings in bipartite graphs, all of these are significantly easier than the corresponding problems in non-bipartite graphs. And especially when we are going to do matchings, we are going to distinguish between these two cases. Okay? Because the level of difficulty is just like significantly greater than what happens in the bipartite case. You will see that when I tell you the particular years in which results were proved. Generally, there's a gap of 20, 25, 50 years between the problems being solved for bipartite case and for all graphs. Okay, so that's one of the main reasons we are talking about bipartite graphs. All right, let's see. Okay, so we have been talking about minimum cost perfect matching, but there is a more fundamental problem, right? Which is whether a graph has a perfect matching or not. So let's talk about that. Somebody had asked earlier, and given yesterday's poll, I decided that we can talk about it right now itself. And then we will talk about it more in future modules. Okay. So I want you to consider the following decision problem. It's a decision problem of whether a particular graph has a perfect matching or not. Okay. Given a graph G, decide whether G has a perfect matching? So I would like to ask you, is this problem in NP? What do I mean? Can you convince your friend easily that a particular graph has a perfect matching? And if so, how would you convince your friend?
Yeah, you can convince.
Okay, and can somebody else tell me how you would convince your friend that a given graph has a perfect matching? Supposing I give you this graph. So how would you convince your friend that this graph has a perfect matching? Provide a perfect matching. Exactly. Right. By finding any perfect, you don't need to find it, you just need to show it. How you find it is the algorithmic question. So this problem is an NP because a perfect matching is a certificate. Okay, any perfect matching is a certificate, right? So whenever the graph has a perfect matching, it comes with a certificate that it has a perfect matching. Now I want to ask you, what about co-NP? How would you convince your friend that a graph does not have a perfect matching? Supposing I give you a graph on, I don't know, 20 vertices, right? Is there any easy way to convince your friend that this graph does not have a perfect matching? So Anand says find the maximum matching, right? Okay. So a maximum matching, but you will have to somehow certify that it is a maximum matching, right? So how will you convince your friend that this is indeed a maximum matching? I mean, in the case of a perfect matching, it's very clear. If I give my friend a perfect matching, my friend can go and check that every vertex is exactly one edge from this set of edges incident at it. But how does someone check whether a given matching is a perfect matching? Why should your friend believe you? Do you all see the problem? Right? Because you need to now convince your friend that the maximum matching is indeed a maximum matching. And because it does not cover all the vertices, the graph cannot have a perfect matching.
So, like, what's a maximum matching?
Oh, good point. So the maximum matching is a matching which has as many edges as possible, right? So just to give you an example, let's see. Consider this graph, right? Clearly, this graph does not have a perfect matching, but it has a matching that matches 4 of the vertices, and it contains 2 of the edges. So you can show that there is no matching with more than 2 edges, right? In this example. So this is a maximum matching.
Oh, okay.
Okay.
Sir, just small
Yeah.
question.
Yeah, go ahead.
Does maximum matching mean an independent set?
Um, no, but
Okay.
it is an independent set in what is called the line graph of the graph.
Okay. Okay. I mean, okay, just seems similar. That's why I just got the question there.
Right. So the complexity is very different. Independent
Okay.
set, finding a maximum independent set is an NP hard problem. In
Okay.
fact, probably NP complete. But finding a maximum matching is a polynomial time solvable problem.
Okay.
But you are right in the sense that it does become an independent set in the line graph, if you know what a line graph is.
Okay. I have no clue about that.
Okay. So anyways, we can talk about it offline. So it sounds related, but it's not exactly the same problem. Right. Good. Any other questions? So how will you convince your friend that a given graph does not have a perfect matching?
So I think we have to iterate over all possible subsets of the vertices and then show that there is no perfect matching.
Sure. Let's iterate over all possible subsets of the edges and
Huh.
check that each of them is not a perfect matching. Right? So this is not an efficient way to do it. Do you agree? Yeah? Would this be efficient or would it be inefficient?
The
It would be
number of
exponential.
subsets.
It's very inefficient.
Exponential, very inefficient, right? So it is exponential, right? So this is not a good certificate. So the point I want to make is that without theorems that do exist, it's not clear whether this problem is in co-NP. It's not clear why there should be an efficiently verifiable certificate. However, many of you seem to have seen Hall's theorem as per the poll which we conducted yesterday. So Hall's theorem does tell you that the problem is in co-NP for bipartite graphs. So the answer to this is actually yes. And for bipartite graphs, you need a result called Hall's theorem. And for the general case, you need a result called Tutte's theorem. But we will talk about Tutte's theorem later. I just want to talk about Hall's theorem today. Okay. So once we discuss Hall's theorem, it will become clear why that is actually giving you an efficient certificate. Okay. So let's start with an example. Consider the following graph. Does this have a perfect matching? If yes, can you find me one? Actually, sorry, I think I made a mistake. I first want to give you this graph. Yeah, my bad. Does this graph have a perfect matching? If yes, can you please give me one? Because that would be the certificate. Zero 0516738294. Yeah, that is correct. Right. So 0516738294. This works. Good. Okay. So that convinces me that this graph indeed has a perfect matching. And now let me draw the graph I actually want to draw. And let's say I put these two edges here instead. Let's consider this as our set A and this as our set, maybe the bottom one is our set A and this is our set B, the two color classes of the bipartite graph. How about this graph? Does it have a perfect matching? If yes, find me one. If no, convince me that it does not have a perfect matching.
Right, if we choose the vertices 5, 6, and 7, the adjacent vertices are only 0, 1.
Right. So
So-
let's look at 5, 6, and 7. That's a good thing to look at. Let us consider this set of vertices. So you are saying that this set of vertices 5, 6, 7 has only two neighbors. Is that right?
Yeah.
Okay, so can anyone explain to me why this is a problem? So there is a set of vertices S whose neighborhood n of S, as we defined in our first lecture, is smaller than the size of S. Can anyone tell me why this is a problem? Someone else, please.
Pigeonhole principle, right?
Sorry?
Pigeonhole principle, yeah. You need at least.
Sure. Right. Notice that in a perfect matching, you will have to match the vertices 5, 6, and 7 into the vertices 0 and 1, right? Because there are no edges between them. That is an independent set, as someone pointed out. There are no edges inside 5, 6, 7. So the only way to match them is to match them to one of the neighbors, right? But there are 3 vertices and there are only 2 neighbors. So that's a problem, right? Does everybody see why this implies that the graph does not have a perfect matching? Right? So, are there any questions or concerns at this point? So that gives us some necessary conditions for a bipartite graph G to have a perfect matching. And one of the conditions that you have pointed out is that for every subset of A, the neighborhood of that subset should have cardinality at least the size of that set. Is there any other condition you need? Do we need any other conditions? What about the size of A and B? Do we need some condition for them?
I mean, B should be same as.
They should both have the same cardinality, right? Because each vertex of A is matched to a vertex of B and vice versa. So clearly the number of vertices in A has to be equal to the number of vertices in B, right? So these are necessary conditions, and Hall's theorem says that these are actually sufficient conditions. In fact, I like to focus on the second condition because that is the most important one. So Hall's theorem from 1935 says that if GAB is a bipartite graph with cardinality of A equal to B, because it is kind of an obvious necessary condition, then G has a perfect matching if and only if, I'll actually state it differently. I'll state it as G does not have a perfect matching. G does not have a perfect matching if and only if there exists a set S subset of A such that the neighborhood of S is smaller than the size of S. Right? So it's saying that this necessary condition is actually sufficient. So whenever the graph does not have a perfect matching, it's because there is a problematic set. Such a set, such a set is called a deficient set, or we might just call it a Hall set. I don't know. It is deficient in the sense that it is very few neighbors. So in that sense, it is deficient, or simply a Hall set. Okay? Good. Does everybody see why this implies that the problem is in co-NP for bipartite graphs? Now, if you want to convince anyone that a particular bipartite graph does not have a perfect matching, you know there exists a Hall set. Remember, we are not asking about how to find a Hall set. That's the algorithmic question. That does not have anything to do with NP and co-NP. We are just saying that there exists a certificate that implies that the graph cannot have a perfect matching. And Hall's theorem gives you such a certificate. Okay. It is worth noting that Hall's theorem was proved in 1935, whereas concepts like NP and co-NP are much more recent. They came about in the 1960s, right? But clearly, results from the past have consequences related to them.
Sir, I had one question.
Yeah, go ahead.
The Hall set is the neighborhood or n of s, or is it s?
Generally, it is S. S is the Hall set. It is a set who is deficient because its neighbors are too few.
Okay. Okay. S
Yeah.
will be the Hall set. Okay.
Exactly. Exactly. Good. Any other questions? Right. So I just want to say that Hall's theorem implies that the decision problem for perfect matchings for the case of bipartite graphs belongs to co-NP. Because now you can convince anyone that a particular graph does not have a perfect matching. Okay, good. So that's all for today. It's already 9:55. Sorry for going up by 5 minutes. So that's the conclusion of the lecture, but I'm here for another 10 minutes if you have any questions or concerns.
Sir,
Yeah,
in the
go ahead.
second condition of Hall's theorem,
Yeah,
have we assumed A like without loss of generality, or using this condition for A, we can prove the same condition
good,
for B?
good. So it is symmetric. So do it yourself. Show that the condition is symmetric in A and B. What I mean is, if there is a deficient set in A, then there is a deficient set in B, vice versa. Okay? Does it answer your question?
Yes, sir.
Okay, so there's nothing special about A. The same thing applies for B. It's just that there is some symmetry in the graph, which is why you don't need to say both statements. Any other questions or concerns?
So, like, if it didn't impose the other condition that the cardinality of A equal to B,
Hmm.
then you can
Right.
use this condition for both A and B and to get that other.
Sure. Yeah. If you did not write A equal to B, you can just put down both of these conditions for both. Yeah, that's right. Because if you put down for both of them, it implies that A is actually equal to B, right?
Yeah.
Yeah, that's a good point. But this is generally how it's stated because it's easier to parse, I guess. Okay, so I hope that after this discussion, this NP co-NP business is a bit clearer. Um, but if it's not, please, this is a good time to ask. Or you can send me a message and we can find a time to discuss it further. I personally feel that having this viewpoint of NP co-NP is very useful in appreciating the material better. This is not a course on complexity theory, but I just feel that having this understanding will help you appreciate the course material better. Also, these are concepts that you will see in all of your theoretical CS courses. So, especially if you are from CS, which most of you are, it's really good to become familiar with these concepts, even if it is an intuitive level and not at a formal, rigorous level. All right, so I'll stop recording now, but I'm still here for another 5 minutes or so.